The class is on inferential statistics. Okay, so I welcome you all once again. The network was having small issue. I just recharge another line so that I can use both for the live stream. So I welcome you all once again. This is ElectroTeach. Today what we are learning is research method, statistical method in research. Statistics. So if you can hear me, please type yes on the screen in the chat box. If you can hear me, type yes. So we are looking at differential statistics. We also have descriptive statistics, descriptive. Now, we all know descriptive statistics. Those are the various ways by which we can describe data obtained. For example, we can calculate a mean, a set of data, mode, median. These are regarded as descriptive statistics. So we use those to describe the data that we have. Okay, so if you can hear me, just type yes on the screen. Okay, I can see many of you are saying yes. So do say yes and give us thumbs up in the on the video, the live chat, so that others can see it online and join as well. So now we want to look at, excuse me, we want to look at the research methods and how we can analyze data. Like I said earlier, our main focus will be on inferential statistics. We are not going to do much on descriptive statistics. Now, mean, we are going to also use mean, which is the arithmetic mean or average in the inferential statistics that we are looking at. So, to describe our data, we can use mean, median, mode as a inferential statistics, as descriptive statistics. And that one can help also to describe the behavior of a set of data. But in order to actually make a conclusion on relationship between two variables, we will need to do more than that. We will need inferential statistics. And these inferential statistics, they are called test statistics in research, test statistics. So we have a few number of them we are looking at today. We have the chi-square test, we have the t-test, we have the f-test, we have the z-test, and we have the ANOVA. We want to look at those ones that we are able to cover today. We may not be able to discuss in full all of them, but at least we are going to discuss 3 or 4 in full today. All right. Now, when we choose a method of test, we also have what we call the tail of a test. Tail of a test. So, for instance, if you formulate hypothesis in this way, mu equals A, then H1, this is fundamental hypothesis and this is a alternative hypothesis, H1, mu less than A, then we say this is a one-sided test, one-sided, and then lower tail rather. lower tail, because this is less than A. Now, if you have the same expression here, then the alternative statistic or the alternative hypothesis says mu greater than A. It's still a one-sided test, but in this case, it is upper tail, as it were, upper tail test, because this is greater than, this is less than lower tail, this is greater than upper tail. Now, if you have H naught mu equals to A and H1 mu not equal to A, then we call this one a two-sided test, two-sided test, and that is two-tail test, two-tail test. So A is a number of consideration in a particular research. That's the number that we consider. That is that A. So it can be any number. If it's a numerical research, we have a quantitative data. So we deal with A as a number. But if it is qualitative, we will not write anything in this manner. We write statements that show our hypothesis, statements that show what we are dealing with in the research, statements will make up our hypothesis. Now, to continue now, we want to look at the procedure we follow in applying some of these test statistics that I mentioned earlier, the inferential statistics such as the Z-test, the F-test, the chi-square test, the ANOVA, the T-test, and F-test. So now we want to look at the procedure. The procedure is that first, after having the research question, research problem, we make a statement of hypothesis. You state your hypothesis. That's the first thing. Before analyzing any data, the first thing to do is to state your hypothesis. First one is fundamental hypothesis, H0. You state it, maybe in a statement or in mathematical form this way. Then you state the alternative hypothesis. And remember, the interest of the research, what we feel should be happening, relationship between variables, will be put in alternative hypothesis, because null hypothesis does not see any difference between variables. Variables are not different, so it doesn't see an influence of one variable over another. But alternative hypothesis shows that there will be a significant influence of one variable on another. All right, let's look at a Z-test. Z-test. If you follow this in your handout, we have a problem that says from extensive records, it is known that the duration of treating a disease by a standard therapy has a mean of 15 days. A mean of 15 days. It is claimed that a new therapy can reduce the treatment time. To test this claim, the new therapy is tried on 70 patients. And from the data of their time to recovery, the sample mean and standard deviation are found to be 14.6 and 3.0 days, respectively. Test the claim using a 5% level of significance. That is the worked example that we want to take first, and we are going to use a Z-test. Now, we apply Z-test, especially when we have a number of data up to 30 or more than 30. You can apply a Z-test. I hope you are following this in your own handouts. So invite others of your colleagues to join us. Invite others to join us. Okay. So if you can hear me, say yes. If you can hear me, type yes on the screen. I want to see that you are hearing me over there. I want to see that you are hearing me. I need multiple responses. Okay, I see some few people typing yes. That's fine. Can you hear me? Say yes. Right. I want to be sure that everybody is hearing me. Now, if you are not hearing me properly, you might need to change your network. Right now, my own network is stable and steady. Like when I started, I have actually got data on another line to back it up so that two of them will be working at the same time. So that's what I do here. Right, I can see many years over there. Okay, so I want you to have a look if you can see, if you can read this. This is a question that we are treating right now, and I've read it out. Excuse me. Now, the claim says the therapy reduces the treatment time. Therapy reduces the treatment time to less than 15 days. That's what the question says. It said the standard time is 15 days, but the therapy reduces the treatment time. That means the therapy is saying the treatment time, the new therapy will take less than 15 days to handle. That statement will be in the alternative. Okay, let us look at the way we are going to write the hypothesis now. First one is Z test that we want to apply. Z test. We're going to apply Z test. Now, hypothesis. First thing is to state hypothesis. H0 mu greater than or equals to 15. You know, the research is focusing on the fact that therapy reduces the number of days. The standard number of days for recovery is 15. So H1 will be mu less than 15. If you look at this formulation now, you see that we have covered all available spaces. We have less than 15 and the alternative, which is the points of interest in the research. And we have greater or equal to 15. 15 and above will be in the null hypothesis. Now, the test statistic that we choose is Z. Z test. And here is the formula for Z test. All right. And then we are told in the question that the average X bar is equal to 14.6. And we are told that the number of patients N equals to 70, right? And the standard deviation is 3. Standard deviation is 3. S equals 3. That's what the question gives us. And then, okay, mean of 15 days, right? Ordinarily, we have mu equals 15. Now, we want to substitute all of this. Then, we are given the problem also that alpha equals 0.05. That is a 5%. Because they gave us, the question says, test the claim using a 5% level of significance. So we must note at what level we are going to test. So it is 5%. So let's look at this calculation now. We can substitute all this into the formula for Z test. Z equals X bar, that's 14.6, minus 15, divided by 3 over square root of 70. Now, the answer to this is 1 minus, it's minus 1.12. All right. Now, we want to look at the value of Z test on the table, on the statistical table, at the level of significance of 0.05, that is 5%. So we turn to the table. You check your table now on page 1. On page 1, you see a table. Now, this particular test is a one-sided test, lower tail, because we have a less than. We have a less than, so it's a lower tail test. All right, so we are going to check you see the small table on the chart. You see lower tail at 5%, 1.645. Okay. And if you can confirm from your own table, you see that we have minus 1.645 because it's on the other side. It's on the other side. Since it is less than, so we look at the distribution charts like this. Anything from here is positive, anything from here is negative. So what we are dealing with is less than, and it's somewhere around here. So minus, it's around the minus 1.645, 1.645 minus, that is this point. So if it is greater than, then it should be on this side. So it should be on that side. So we see minus 1.645 on the table. If you check your own table carefully, you will see that the answer on the table is 1.645. But how did we know it's minus? Because we have a less than here. And this is 0 points. Anything on this side, if it is greater than we have, then it should be on this other side. All right. So what we are going to do is to compare this value to this value. Which one is greater? You will see that our own is somewhere around this point, minus 1.12. That's what we calculated. So the table value, you know, is on this side of the calculated value. So what we do now is to make a conclusion, because Z, our Z, and is minus 1.645. So we can accept null hypothesis because our own is higher in value than the table value. What we calculated is higher than this because it's minus 1 point, and this is minus 1.6, minus 1.1, and this is minus 1.6. Our own is higher than the table value. So for that reason, our conclusion will be that we accept null hypothesis. We accept H naught, and that says that the treatment time is greater or equal to 15. That the new therapy does not reduce the recovery time, you know, below 15 days. That the 15 days will still be needed for a patient to recover. So we accept H naught, we cannot reject H naught. So if you follow from your own handout, that's what we have. All right, let's take another one here. The second example says a machine is set to produce bolts with a mean length of 1 inch. Bolts that are consistently either too long or too short will not meet specifications. Now suppose n is equal to 50, that is number of bolts 50 are sampled, and the average length is 1.003 with a standard deviation of 0.01 inches. Is there sufficient evidence at the 5% level of significance to conclude that the machine is producing bolts which do not meet specifications? So we want to test this one also statistically. So having got this one, let's go to the second one. The second one also we will write the hypothesis. So for the hypothesis, that is the first part to start from. Hypothesis, mu equals 1.0. That is null hypothesis. Alternative hypothesis, mu not equals 1.0. So because we have not equal here, this is going to be a two-tailed test. So what we are looking at is machines producing bolts that are not equal to 1.0. That is, either they are less or higher than 1 inch. But null hypothesis is telling us that the machine is working fine. There is nothing wrong. So mu is equal to 1.00. That every bolt produced of 1 inch in size. That is what null hypothesis is saying. But we want to test, our real interest is that this machine is not working fine. We want to confirm that the bolts being produced are not 1 inch exactly. So we can apply Z test because any is equal to 50. And I told you we can apply Z test when n is large, 30 or higher. So we choose the Z statistic once again at 5%. Now, before we go, we are told that n is equal to 50. That is correct. And then average length x bar equals 1.003. Then standard deviation equals 0.01. Those are the values given. So we can apply this Z test. X bar minus mean divided by S divided by square root of n. So if you substitute these values, you can have Z equals 1.003 minus 1 divided by 0.01 over square root of 50. And the answer is 2.12. Now, because we are dealing with double take tests, when we go to check the table, we also bear that in mind. If you go back to the table now, under 5%, alpha is equal to 5%, that is 0.05. If you go to the table now, you go to double tail. And so when you check that, what you, excuse me, when you check from your table, you can cross check from your own table, you will see that the answer is 1.96. So table value 1.96. Or calculated value is 2.12. Right? So now we can see that our calculated value is higher than the table value. Is higher than the table value. The first one that we did, our calculated value is lower than the table value. But here, 2.12 is greater than 1.96. So for that reason, since it's a two-tail test, we split the alpha into 2.5. For two-tail now, then our alpha will be 2.5%. So we check under 2.5 because we have a two-tail test. Check under 2.5, then you will see that the alpha value is 1.96. That is how we obtain that under 2.5. Okay? Under 2.5. Now, we want to make a conclusion. Next thing is to make a conclusion about that calculation. What will be our conclusion? So we reject H naught because what we calculated is higher than what we saw on the table. So we reject H naught, accept H1. And that is the conclusion there. All right. Accept H1. That is about Z test. That is how we apply Z test. Now the next one will be another test statistics, and that is a chi-square test. Chi-square test. All right. So you can hear me. I want to see you say yes. Type yes once again. If you have questions, ask questions. Ask questions. Somebody is asking whether this is a class work. It is. Since we are not able to meet a class one-on-one, we talk on the live class like this. So I want your responses. Here, Mrs. type yes. Ask questions. So type yes. And follow this up in your own handouts. Follow it on handouts. Now, this is what you decided to have. So there's no problem about that. We continue. Chi-square test. Chi-square test. These examples, the work problems are also in the handout that you can follow from your own end. So now we go on to chi-square test. This is written like chi, but it's pronounced chi. Chi-square test. Okay. So from with a chi-square test, we are able to observe the differences in frequency, the observed frequencies, and the expected frequency. When you are given a data, there's something you expect that will be happening from one set of value to the other. That is one variable over the other. So the chi-square will help us to detect whether there's an influence of one variable over the other, what we observe and what is expected. So that is why a chi-square test for 2 by 2, the 2 by 2 is the one we are going to deal with first. The 2 by 2 has a 2 by 2 table. We have a data type. We have question type. We have possible response. And so this will now give us sets of value like this, 4. Then we are going to do a summation, that is the total for both the column and the row. So this is a 2 by 2 contingency table. Now the 2 by 2 contingency table, the total column and the total row will not be here. We have values in A, B, C, D. 4 values will be given. And the 2 by 2 contingency table is the simplest to handle, because you calculate the chi-square, which is represented as X, this special Greek letter looking like X. We are going to use it simply as this. AD, that is this times this. Okay, let me complete the table first. Let's do a summation of this, A plus B, C plus D. That is what the candidate will do by himself. The table, the question will give only A, B, C, D. Then you do the summation yourself. A plus C, then B plus D. Okay. So now use this formula as chi-square. AD minus BC squared multiplied by A plus B plus C plus D. Now this particular portion is summation of this, or summation of this, which is A plus B plus C plus D. All right. Divided by A plus B, that is this one, multiplied by C plus D, this one, multiplied by A plus C, and multiplied by B plus D. This is for the 2 by 2 contingency table. 2 by 2 contingency table, that is what we have. So when we have 2 by 2 table given, this is the formula to employ. We complete the table by doing the total of the column, total of the row. You know, these are the total for the column, A plus C, B plus D, total of the row, A plus B, and then C plus D. Then total of everything is here. That's how all these values in the formula, we have gotten them from the table. There's nothing to imagine where it's coming from. They are actually on the table right here. So let's take one example. All right. One example on the handout says, suppose you conducted a drug trial on a group of animals and you hypothesize that the animals receiving the drug would show increased heart rates compared to those that did not receive the drug. You conduct the study and collect the data as follows. So we now have a data that is put on the table in this manner. So let me just edit this table here to show the problem given here. Heart rate increased. And then no heart rate increase. Okay. We have 36, we have 30, we have 14, we have 25. Okay, so this is the problem given. Then the problem says this is treated and this is non-treated, not treated. So these are the data given. So to proceed, what we first do is to do the summation, the total for row and column. For this column, for this column, for this row, then we do the total summation here. So we sum this, we have 66, we have 39 here, we have 50 here, we have 55 here, and the total summation is 105. Then we write this formula just like this and put in the values. So remember, the problem given is only 1, 2, 3, 4, A, B, C, D. Then you're going to complete the table by doing the total for the rows and the total for the columns. Then you apply this formula. So if you apply that, if you follow from your handout, you see that we have 105 multiplied by 36 times 25 minus 14 times 30 over 50 times 55 times 39 times 66. And the answer is 3.418. 3.418. That is the chi-square for that problem. Now, remember, before starting the solution, you need to make hypothesis. And the hypothesis stated here in this example is this: H0, that is the null hypothesis. The proportion of animals whose heart rate increase is not dependent of drug treatment. That is independent of drug treatment. Null hypothesis says the heart rate is not as a result of the drug employed, the drug administered on the animals. Then the alternative hypothesis: the proportion of animals whose heart rate increase is associated with drug treatment. So that's our main goal. We want to show that the new medicine administered on the animals is causing the heart rate to increase. Because if you look at this table, this is 36 and this is 14, no heart rate. And then 30 here, 25 here. Although these are not treated, these are treated. So our interest is that heart rate increase that we see here, this high number, is due to the new drug for treatment. So that our objective I want to show will be in the alternative hypothesis. So the null hypothesis states that there is no influence of this drug on animals. It doesn't increase their heart rate. Now we've got that. Then we go to table. The next thing is go to table because we have calculated our chi-square. So we go to table under 5%. You go to table under 5%, you will see that what you will see is 3.814 table value. Table value 3.814. Now, if we break it down, you see that the p-value is above 0.05 because the real table value will be between 2.706 and 3.841. So we can see that our p-value is greater than the 0.05 significant level. Okay, sorry, this is the calculated value 3.418, and the p-value is 0.065. The p-value is 0.065, which is actually greater than 0.05, and this is a 0.065 greater than 0.05. So our own p-value is greater than the standard 5%. For that reason, we fail to reject the null hypothesis. And what do? We accept the null hypothesis. That's the conclusion. So your conclusion, you will say that we accept the null hypothesis and reject the alternative hypothesis. We accept the null hypothesis and reject the alternative hypothesis. Now, I'm going to give another example which is not initially in the handout. Having got this solution, the one I'm going to bring up now is going to be a new problem that we are going to solve together here. If we say we have 3 fellows that work for one man and he gave them money. Let's say he gave them 2,000 naira. 1,000 naira, and we are going to share it between the 3 of them. But we found out that they didn't share it equally. So we have Kunle, we have Tope, and Shade. So this man gave them 2,000 naira, and then they share it. When they share it, we now have a table this way. Kunle, Tope, Shade. So let's say Kunle, instead of sharing it equally, they say that okay, there's no way they can share 2,000 naira equally. Kunle now say, okay, he worked more for that man than the other people. He took 900 naira out of 2,000. There will be one remaining. Then Tope took 600 and they gave 500 to Shade. So these are the observed. Okay. So we call this data given here the observed. And then we want to now know what is expected. So you call this one observed. And this is expected. We want to look at expected. Now, okay, let me change the data. Let me change the data to 15 so that it will make the calculation easy. Let's change the data to 15. Out of 15, the first person took 700, and then the second person took 500, and they left 300 for the last person. That is 15. Yes. So, but for calculation to be easy, that's why I changed it. Now, under expected, what we expect is that they should share this money equally. Each person will get 500, 500, 500. That is under expected. Okay, you can see hear me. I want to see your yes. All right. I want to see your yes on the screen. If you can see, hear me. I want to hear your yes. Let's say we're on the second example under chi-square. This particular one has its own formula. Its own formula is different, and that's why I'm going to show how to use that formula. Now, I'm going to use that formula, which is a new formula. So we have this observed and expected. This is observed. This is what we observed that really happened. Or this is what we expect that will happen. Because if you share it equally, you get 500. But since they did not share it equally, we have 700, 500, 300. So the new formula we are using says chi-square equals summation of observed minus expected square from k to I. Observed minus expected all squared. Everything divided by the expected. So what we are doing is this. I'm going to do what is inside these brackets on the table. I'm going to determine by calculation what we have here on the table. So what we are going to have is this. So the question given is this, without this 500, which is expected. So in the question will give you the data like this, telling you the total, and then sharing it this way, that is observed. Then you are going to do the expected column yourself. You're going to create the expected column. Now, let's now look at what will be observed minus expected. O minus E, then we square it again, O minus E squared. Then we have O minus E squared, then divided by expected. Divided by expected. O minus E squared divided by E. And when we finish with that, then we do a summation of it, summation of this last column. So O minus E, 700 minus 500, 200. 500 minus 500. Okay, let's leave it like that, but this one will give us 0 anyway. Maybe I should change it from 0. I don't want 0 value. I don't want 0 value. Let me give it 400, and then let's say 450, and then 350. I don't want 0 value in order for you to understand the calculation well. So 450 minus 500 minus 50. 350 minus 500 minus 150. Okay. That is it. Then we begin to square them. All right. Yes. So if you are still following, just be watching what we are doing here, because you see so many other examples or tutorial problems based on this. So we square them. We have 4,000. We have 2500, and we have multiply 150 by 150 now. What do we have? So somebody should write the answer on the screen. 150 squared. What do we have? So we multiply 150 by 150. We use my calculator here. But I want to see that you are following. What is 150 multiplied by 150? Can somebody type it on the screen? Are you following? Let me see your answer on the screen if you are actually following. 150 multiplied by 150. Type the answer on the screen. Use your calculator, and then put your calculator by your side, because I'm going to do the next one also based on calculator, and then it's not something you can be doing offhand. Most of the questions there, most of the calculation there, it's not by offhand. Somebody said 22500. Somebody to put minus there. My dear, it is not minus. There is no minus there. It is this value that we are squaring up. Minus multiplied by minus will give us positive. Minus and minus here give us positive. So there is no minus in that answer. So please take note. We are squaring what is inside this column. That's why we are getting this. Look at the column here. O minus C all squared. So if you are putting minus 22500, you are wrong. Take note. Don't do that in the exam. I have seen that error in the exam over and over again. That somebody will multiply this and put minus A. And at the end of the day, when you finish this division, the total answer is going to get for the chi-square will be wrong. Please take notes. There's no minus there. There's no minus there. So 150 times 150, or minus 150 times minus 150, is 22500. It is not minus. The next one, we now use this column to divide this column. That is O minus E all squared divided by E. 4,000 divided by 500. So what's your own answer? I'm doing it. I don't want to wait again because of time. Then 2,500 divided by 500. What's your own answer? Two to 500 divided by 500. What's your own answer? Mark you, this column divided by this column, not divided by this, divided by E. This is E expected. O minus E all squared divided by E. That's what we are having here. Are you following? Okay. So what we now do is this. We now do a summation of this last column, and that is our chi-square. Look at the following formula. Formula says summation of observed minus expected over expected. This is a square. That's a square here. Sorry for the way the board is small. The board is small. Observed minus expected squared divided by the expected. Then we take a summation of that. Check the formula again. And the answer is 58, isn't it? What did you get on your own? What did you get on your own? 45. Okay, that's the last one. Then summation of everything is 58. And that's our chi-square. Chi-square, written like a big X like this, is equal to 58. So based on this, we can now go to the table and check the table value. And then when you are checking the table value for chi-squared, we look at what we call the degree of freedom. Degree of freedom. Let's say we're still using alpha of 5%. DF, what is our DF? DF is number of rows minus 1. Number of rows minus 1. Now, if you have a data that has 2, we have rows and columns. Now say number of rows minus 1 multiplied by number of columns minus 1. For this instance, we have the data given is only 3. So we have 3 minus 1. Okay, that's n minus 1, and that is equal to 2. Degree of freedom is equal to 2. We need the degree of freedom and the alpha level to check the value on the table. So we compare the value on the table with the value we calculated. So we look at which one is higher, which one is lower, before we make a conclusion whether this money that they shared it very well, or somebody actually cheated someone. Our intention is to believe that somebody is cheating. Look at it. Somebody collected 700, somebody collected 450, and the last person 350. Look at the difference. So our aim in this finding is that money was not equally shared. So you will first of all state your hypothesis that H0, there is no significant difference in the money shared. That is H0, no significant difference. Even though there's a difference, but the statistics assume that the hypothesis we assume that there is no significant difference. Then we can also say H1, state our H1. There's a significant difference from the money shared. So we now use that one to check table. So table value, that is chi-square value table now. You enter chi-square value table. Under chi-square, if you check the soft copy given, you will see the degree of freedom under 5%. Then you pick out the answer. When you pick out the answer for that, then you compare it with what we have. If what is on the table is higher than this, that means we can actually make a conclusion that H0 is right. There's no significant difference. But if the table value is less than this, then we can say there's a significant difference. So we reject H0 and accept H1. Now, this is a hypothetical question that I just set up now. And so I'm not going to make the conclusion. I want you to make the conclusion, and perhaps you can type the answer of the table value you got. Type the answer for the table value that you got on the screen. Yes. But then there's another third type of chi-square problem that I want you to also know about. another type of chi-square problem that is not as straightforward as the 2 by 2 contingency table, that has another approach. And the formula is see this. Formula is see this one. But the approach is different, slightly different from this. Because here we are giving data of only one column only. But in this particular question I'm going to bring up now, I'm going to have two columns. So we are going to use that one too as an example. I hope you are still following. All right. What's the question, please? Can you bring up the question again? Somebody is asking a question. Somebody is asking about the expected. The expected, look at this coin here. Let me bring it up. We have observed, this is the data given. You know, this 500 is not given. Understand? This data is given. 1,500 is to be shared between these three people, and they have shared it this way. That is the observed. Okay. So you use your common sense by dividing that money with the number. We have three of them. 1,500 by 3. You get 500, 500, 500. And of course, you can write it there if you want to do it, but you can only make the column to be larger a little bit. So you write any over 3. Sorry, total over 3. Just write 15 divided by 3. 500, 500, 500. So somebody that, I hope you got it now. Somebody that say, how do we get the expected? That is how to get it. Somebody is asking about the alpha. I told you earlier that a significant level is always given in a question of research like this. If it's not given, you are going to use 5%. 5%. Now, usually each problem will come with its own significant level. So this problem comes with 5%. Then degree of freedom, we look at number of columns and number of rows for chi-square. To check the value from table, we need the degree of freedom. We need the degree of freedom for a chi-square problem. Are you with me? To get the value on the table, you will need the alpha and the degree of freedom. That is how to get it. So your alpha has been given, but degree of freedom will be calculated by yourself. And it is easy to calculate because df equals n minus 1 multiplied by c minus 1. Number of column, number of row, and number of column. So we have in this problem, this is not there. We have only one, row or column, and that is how I got it. That n minus 1 is equal to 2. But in a problem that we have rows and column, we are going to have this way: row minus 1 multiplied by column minus 1. And the example I'm going to give now, we're going to use that. We're going to use that. We're going to have rows and column. So the person that asks about degree of freedom, that is how we got it. And we need that we can get value from the table that we're going to use to decide, make a conclusion about the data that we just examined, that we just analyzed. We're going to make a conclusion whether there's a significant difference or no significant difference. Okay. For instance, the one we just finished, if you have your statistical table with you, you can check the chi-square table. Check the chi-square table. You will see that you will need degree of freedom, which is regarded as a V. Are you there? Regarded as a V. Okay. Can you check your statistical table? So if you check, I want somebody to look at the statistical table now. I'm checking mine here. You see page 9, we have chi-squared. Have you seen page 9? Page 9. Table 8.4, we have chi-squared. We have degrees of freedom, 1, 2, up to 10. Then we have 5%, 1%, 0.1% as a row on top. Then each column have 5%, one column 5%, another one 1%, another one 0.1%. Then column 1, we have 1, 2, 3 up to 10. That is degrees of freedom. So if you check the degree of freedom for this solution that we had, our degree of freedom is 2. So we check on 2, and if under 5%, we have 5.991. Table value 5.991. Can you confirm from your own table? Can you confirm? Somebody said 2.92. No. Degree of freedom is 2. And then alpha is 5%. Check under 5%. And then check under degree of freedom 2. 5.991. That's what you have. You can check again. Can everybody check and confirm? Can somebody check and confirm again? 5.991, yes. I can see many people typing 5.991 now. And then some are saying hi. Just continue to like this live stream and invite your friends. I can see that we have less people connected. Invite them, let them connect. Let them connect. We have about 40 people connected at a point. We're having less number of people now. Right now, I'm going to another example. Now, before we go, let's make a conclusion here. Our calculated is higher than the table value. So we reject H naught and accept alternative. That is it. Alternative shows that there is a significant difference in the way this money was shared, that it was not shared equally enough. That's the meaning. Now we want to look at another example whereby we have rows and columns on the given problem, and we are going to solve that problem using chi-square again. So I'm going to give you another table of another problem which requires a new approach. But let me leave this formula because we still need it. Let's say we have two departments, electrical, mechanical, and civil. Electrical, mechanical, and civil. We want to find out whether sex influence students' selection of these departments. Does sex influence the selection? So let's have it this way. This way, we have male, we have female. Does sex have anything to do with student choice of course of study in engineering? This is also a hypothetical case I'm bringing up. So number of people in each department. Number of people in each department is given here. So for electrical, let's say we have 30, we have 28, we have 25, and then the female, okay, 5, 8, 6. So the problem now says that we want to find out using chi-square at 5% of significant level whether gender, male or female, has an influence on the choice of course of study. So that's what we want to deal with. We want to know whether gender has an influence. So we look at the kind of this kind of problem, and then we look at the solution to that also. Now look at this table. We have rows and columns. It's different from the last one that we have only 3 rows only. Here we have rows and columns. The solution still comes down to the same formula: summation of observed minus expected multiplied divided by expected. And we sum everything up. That's the chi-square. That's the chi-square. Okay. But then we need to calculate the expected. What we have on this screen is the observed. We have the observed on the screen. But what will be the expected? The expected is what we are going to calculate in a different way. It's different from the way we calculated the last one. So let us see what we have here. So we are going to do total summation of rows and columns. This is not 2 by 2 table, but we still need to do total of rows and columns. So we have this is the solution now. That is after you have actually stated your hypothesis. Remember, hypothesis is important. And if you want to state hypothesis here, you can say H naught gender has no influence on students' choice of study or course of study. Then H1 say gender has an influence. Gender has an influence. Because when you look at the table, you see that there are more males in each department than there are females. So somebody will say, okay, it is because they are male, that's why they are coming to engineering, and female, they are running away. That is our interest. That's what we want to believe. So we put that one in the alternative hypothesis. Look at it. Gender has an influence, on the student choice of studies. So that is a hypothesis. But then, in the solution, this is the problem given. You are going to do the total to calculate the expected. The expected is going to be calculated in a different way. Total of this, 35. Total of this, 36. Total of this, 31. Then we do this total also. 55, 75 plus 8, that is 83. 11 plus 8, that is 19. Okay, then we sum this and get it here, or sum these three and get it here. It's the same thing. Okay, 90 plus 12, 102. 102. So having got that, then we will go ahead and do expected. We're going to do expected. So the expected is going to be calculated in a different way. So I will need to rub this hypothesis formulated here. We need to rub it because I need more space for this calculation. Okay. So now I'm going to write the formula of interest for this particular expected calculation. The formula is a little bit developed over, is a development over the ordinary formula that we have. The ordinary expected, summation of expected. So let me give you the formula here. Chi squared equals summation of O R comma C. This is observed. That is subscript R comma C minus E subscript R comma C squared divided by E R comma C. So what are we saying? We are still using the chi-square formula, but modified because we have longer set of data. It's not only 4, we have about six data sets provided. So for that reason, we need to use the expanded formula. This is the expanded formula. ORC means observed row, comma, column. That is, let's say, row 1, comma 1. That is observed 1, comma 1. Observed 1, comma 2. That is, this is 1, comma 1. That is row 1, column 1. Row 1, column 2. Row 1, column 3. Are you there? Then come here, row 2, column 1. Row 2, column 2, row 2, column 3. So that's how we have this formula. So we're going to use this formula to do the calculation for the expected. And when we get the expected, then we do a summation, a subtraction of this, square it, and then divide it by expected. So how do we get that? We do the first one, expected, the first one, E1, we are going to have many expected because we have 6 data. So let me say we are going to have 6 of them. 6 of them. I will just write them 1 up to 6, and this is the way we are going to get it. So we look at the this and this, the total for the row, total for the column, then we use it to do the calculation. Okay, total for the row, total for the column, then you divide it by the grand total. Okay, you need to divide the grand total. That's how it is. Total for the row and total for the column. Look at it. We have 30, 83 here, 35 here. So we are going to use it for each one of them. That's what we are going to do. The grand total is 102, and we need a calculator here. Okay. What is expected for each one? We use row multiplied by column, row, column, divided by total. 83 multiplied by, okay, multiplied by 35, divided by 102. Let me see the other marker here. The marker is going out. I need to bring the other one, the new one again. So somebody should bring out the calculator and be confirming what I will be doing. Are you with me? If you are hearing me, please say yes. Okay.